You ever wonder if you could actually see attention? I mean, not just guess, but really measure it. Well, today we're going to dive into a pretty incredible device that tries to do just that. And it does it by tapping right into the electrical symphony of the brain. So let's see how it works.
All right, first things first, let's set the stage. I mean, why would anyone even need a device like this? Well, the problem it's trying to solve is something I think a lot of us can relate to, especially lately. Just picture this. You're a teacher, right? And you're staring at a screen full of faces. Or maybe just a bunch of black boxes with initials. Are your students actually listening? Or are they, just there? This turned into a massive headache for teachers everywhere. Yeah, that huge, sudden shift to online learning really put a spotlight on a big problem, didn't it? We lost that gut feeling, that connection between a teacher and a student. And it created this real hunger for new tools to try and fix that. And that, right there, is the whole inspiration for the tech we're going to break down today. Okay, so how on earth can a piece of hardware tell if you're paying attention? Is it magic? Nope. The answer is actually in the tiny little electrical signals your brain is firing off. Literally, right this second.
Yep, that's right. Your brain is basically a tiny biological power plant. And the way we listen in on all that activity is with a technique called electroencephalography, or let's just call it EEG. It's pretty straightforward, really. You just place these little electrodes on the scalp, and they can actually pick up the super faint electrical buzz from your neurons.
And this isn't some brand new sci-fi tech. We're talking about building on over 100 years of discovery. It all started way back in 1875 with studies on animals. But the real game changer was in 1924, when a guy named Hans Berger managed to record the very first human EEG. Then, about 10 years after that, other researchers confirmed his work and they really honed in on one specific pattern, a rhythm they called alpha. And here it is. This is it. I know, it might just look like some squiggly lines on a piece of paper, but what you're looking at is a monumental moment in science. This is the first time anyone ever saw the electrical life of a human brain. That top line, that's the EEG. The one on the bottom is just a little 10 hertz timing signal they use for reference. So cool. Okay, so what's the big deal about this alpha rhythm? Well, alpha waves are just brain signals that pulse between 8 and 12 times a second. Simple enough. But here's the magic trick, the key to everything. The strength of those waves, their power, has an inverse relationship with how focused you are. Let me say that again, because this is the most important part. When your mind is just chillin', you're relaxed, maybe a little sleepy, your alpha waves get really strong, really tall. But the second you focus on something, they get weaker, they shrink. And that one simple fact, that is the entire basis for this whole device. Okay. So the science is solid. We get it. But how do you go from that scientific principle to an actual practical gadget? Something cheap enough that a student or a teacher could actually use it? Well, let's check out the design. So the whole idea here is to make it super simple and not, weird or invasive to wear. The concept basically hides the EEG electrodes inside a comfy headphone-style band. So on the back, you've got the sensors reading the brainwaves. And then right on the front, you've got a simple little row of LEDs to give you a quick visual on the person's attention level. Easy. So that tiny little brainwave signal goes on a heck of a journey to become a little blinking light. Let's follow it. First, that super, super weak signal gets a massive boost. It gets amplified. Then a filter steps in and throws out everything except those 8 to 12 hertz alpha waves we care about. Next, a peak detector turns that wavy signal into a nice steady voltage. And they do this for 4 different spots on the head, then average them all together to get a really stable reading. And finally, that final voltage is what tells the LEDs how many of them should light up. Pretty cool, huh? And this diagram really shows you that two-step process perfectly. Over on the left, you've got what they call the initial stage. See how those 4 separate inputs each go through their own little processing line? They all get amplified, filtered, and detected at the same time. Then on the right, you have the collection stage. That's where it takes those 4 results, mashes them all together into an average, and that's the final signal that goes to the LEDs. It's a really smart way to make sure the reading is accurate and not just some random fluke. All right, so the design seems solid, at least on paper, but the big question is, does it actually work? Let's dive into the simulations and see what happened when they tested it with different brain states. So they basically tested 2 opposite scenarios. First, an attentive state. The brain is focused, working hard, and those alpha waves are nice and weak. And second, a drowsy state. The brain is calm, relaxed, and those alpha waves are booming. Okay, now this is really cool. What you're seeing here is the actual output from the filter. That green line, that's the alpha waves from the attentive brain. Look how tiny those peaks are. Now look at the blue line. That's the relaxed brain. Whoa! I mean, the difference is just night and day. Those alpha waves are way, way stronger. And here it is, the big finish. On the left, those big, strong alpha waves from the relaxed person, they result in a higher voltage. And because of that inverse relationship we talked about, that means low attention. Only one LED lights up. But on the right, the weak alpha waves from the focused person give a lower voltage, and that means high attention, so 2 LEDs light up. It works. The system actually works. Okay, a successful simulation is a fantastic first step. That's huge. But going from a simulation to a real physical device that you're going to put on someone's head, well, that brings up some really serious challenges, especially when it comes to safety. So, first off, you have to deal with just how faint these signals are. The brainwaves we're trying to pick up off the scalp are only about 10 to 100 microvolts. To put that in perspective, a regular AA battery is 1.5 volts, so we're talking about a signal that is millions of times weaker. It's so tiny that it can easily get completely lost in all the electrical noise that's floating around us. And the number one enemy here is something called common mode interference. You know that low hum you can sometimes hear around electronics? That's it. It's the 50 or 60 hertz buzz from every power outlet, every light, every device in the room. For a sensitive EEG circuit, trying to find the brainwave signal inside all that noise it's like trying to hear someone whisper during a heavy metal concert. It's almost impossible. So to fight this, engineers came up with this really brilliant trick called a right leg drive. It's so clever. What it does is it measures all that background noise, takes that signal, flips it perfectly upside down, inverts it, and then gently feeds that inverted signal back to the body. So you have the original noise and its perfect opposite. And what happens when you add them together? They completely cancel each other out. Boom. The noise just disappears, leaving you with a much cleaner brain signal. But even more important than cleaning up the signal is safety. And when you're hooking electronics up to a person, there's one rule that is absolutely non-negotiable: galvanic isolation. All that means is you have to create a complete physical break between the electronics and the person wearing them. It's like an electrical air gap. The data can get across, but there is absolutely no way for dangerous electricity to cross that gap. And this isn't just some abstract idea. It's done with real hardware. You can buy these things right off the shelf. Devices like these, network isolators, are built for one purpose: to create that safety barrier. They make sure that even if the main device completely fries itself, there is zero chance of the user getting an electrical shock. Look, this kind of technology is just incredibly promising. You can see it being used not just in classrooms, but in all sorts of fields. But it does leave us with a pretty deep question to chew on, doesn't it? As we get better and better at literally reading what's going on inside someone's brain, we have to be really, really careful about how we use that power. So what do you think? Where's the line?